So just a little bit, what I'm going to cover today, some stuff on electrical safety, some really basic electrical engineering concepts. I am going to use some math. There won't be a quiz, hopefully, and my intention is to really give you an idea of the relationships, not to teach you how to calculate a lot of stuff. Electrical measurements is something that a couple of people have mentioned to me, that how do I use this crazy thing that I bought off of Amazon, and what does it mean for that? And then we'll get into a couple of really nuts and bolts kind of topics on things that are really pertinent to you about putting together the electrical systems on your layouts. I think that'll pretty much fill the time available. There are a few things. I don't intend to talk about DCC much. I'm not much of an expert on it, and it's a subject that could easily fill a whole clinic by itself. And then that's one of the main ones. And this is, I put part one, if there's interest and people want to talk about some of these other things and continue this on, I'd be more than happy to share what expertise I have on that in future clinics too. So let me have your feedback about whether what I covered was pertinent, and if I missed things, what you may want to talk about in any future one, or if you want to say, get rid of this guy, give this guy the hook. We put him all to sleep. So personally, been a model railroader since around 1971 as a teenager, and let's see, you in and out of the hobby, NMRA member though, only for about a year. Actually, this last year's 2024 version of this meeting was my first meeting ever as a NMRA member. As far as background in electronics, I started as an electronic technician a long time ago. And eventually I made my way. I was a senior engineering manager at General Electric when I retired about a year ago. And my personal expertise in engineering, I was an instrumentation and controls engineer, which meant I dealt with remote monitoring and process automation. I'm an electrical engineer by academic training. So it's all pertinent. And along the way, I was a licensed main professional engineer in control systems. So I have some modest amount of experience with this, and then just a little example of some of the stuff you can do. And everybody is capable of this. I think some of it, the topic, people are intimidated by it because they don't understand it, and hopefully I can remove that intimidation so you guys can go, because anybody can build something like this. It's not that hard to do. So let's see. So I'll hop in here. I think it's important to talk about this. Maybe in a lot of cases we don't talk too much in the hobby about some of the hazards we deal with on a regular basis. Electrical being only one of them. A lot of toxic chemicals that we potentially have access to, but nice little graphic thanks to the U.S. government. This is from a movie, one of the first movies they showed us in boot camp in the Navy, Your Deadly Shipmate. And it is quite so. Two main things that we deal with in model railroading is the house current that we all used as the primary source of energy. It can and will kill you if you mess around with it. Easily kill you. I mean, it takes about 100 milliamps of current to be fatal, and with 115 volts, I mean, the smallest household breakers trip at 15 amps. So basically 150 times what it takes to kill you. So your breaker is not going to protect you if you get across it. It's not intended for that to begin with. It's there to keep your house from catching fire. It protects the cable that goes from your box to whatever it's plugged in there. So a ground fault current interrupter is intended to save you. If you happen to have those, they're a good idea. A lot of us have our layouts in the cellar. Recent code, newer residential construction, GFCIs are required for those type of circuits. So they are intended to protect you from electrocution, but I wouldn't guarantee that you have them. Might not be a bad idea to backfit your layout with them. With that, main thing I want to say is, if you're not comfortable with this and you don't know, hire an electrician if you're modifying your 115 volt things. It might save you, some big time grief. And one other one is like the third leading cause of residential fires in the U.S. is electrical. That doesn't mean people doing something wrong, but it's risk versus reward. You might want to stay away from the 115 volt side. Good news is once you get past the plug to just about anything we use in the hobby, you don't have to worry about. We get into this roughly 12 to 24 volt DC range, which is pretty safe to handle. You think about it, we have two bare conductors exposed all over our layouts, come into contact with them all the time. There's not enough energy in it to really to be much of an issue. I would, don't work on the 115 volt side energized. Not worth it. Leave it alone, right? Unplug it, turn it off, whatever you have to do. On the DC side of your power, you're safe to work on it, energized. Sometimes it only makes sense. You're trying to, troubleshoot something. But you also, one thing to keep in mind too is you might want, if you don't really need it energized, turn it off, because you can do more damage. You get in something, you short something you shouldn't have, you can blow up a decoder, you can fry a board in your command station. Some of the especially the smaller electronic devices and decoders in particular are really susceptible to voltage spikes that you can inadvertently cause. So if you're doing something with like that, you might want to consider turning it off, even on the DC side. But for you, you don't have to really worry about it as a safety hazard. One thing I did want to mention, maybe change the format. A lot of times in these clinics, we say, we hold your questions to the end. And I think in this kind of topic, if you have a question, it might be good to throw it out while it's fresh in your mind, and we can see what we can do to. So let's see. So now, got to get a little bit into the theory here. And our good friend George Ohm, you may have heard Ohm. You may or may not know that is a real person. He was a 19th century German physicist, and he came up with this thing, Ohm's law. This is really foundational to much of how our modern world functions. And basically it's the relationship between voltage, E, that's an electrical engineering construct. I don't know why V was already taken for something else, so it's usually called E. Current, I, and resistance in ohms. And that relationship, really simple, really basic, but powerful relationship. It's kind of one of those E equals MC squared kind of things. It's like everything electronic in the world really runs off of this relationship here. So, and then this, you don't have to remember all this stuff, but it's basically just algebraic manipulation. So any two of them, you can figure out that third, and it makes a difference. So voltage, potential, that's the the force behind the what causes current to flow, potential energy. Current is the actual movement of charge through a circuit. So the actual, moving the energy from one place to the other, and the resistance is the impedance to that flow. And the physics behind this are really similar, or not similar, the same as any other energy flow. So if you can visualize how water moves through a pipe, or flows from downhill, electricity works the same way. It's just a different form of energy and a different medium for conveying that energy instead of water. So that's a visualization thing that I've used for years, just get from one place to the other. So this will, as we get into some of the circuit piece, this will be more useful. You'll see how we do it there. The other piece that's not part technically of Ohm's law is power. So power is equal to current times voltage. So the neat thing about using power is, as you move through a circuit, you may change things as you can increase voltage or decrease current and things like that, but power will stay constant. So it's a useful thing to be able to calculate and then use it potentially to extrapolate what's happening in another part of the sun. So, talking about when you're looking at components and you want to put an LED and it's in, and it says, well, it's rated at half of, whatever it is, 10 watts or something, usually pretty low, power for LEDs. And you want to know, well, what do I need to do? And Tom, you mentioned this. Well, the way you figure out if you're safe, you need in that is usually we put a resistor in series with that, so that the power drops across the resistor. The current will be the same through them, and then you can tell, by using this relationship, and I'll show you in the circuit a little better, we'll explain a little better, by using this relationship between current and voltage in the circuit, you can tell what the power will be on that LED, and that'll tell you whether you're within the rating of it or not. So a little bit about circuits. And I'm talking mainly DC here because the concepts are a little easier, but this is completely applicable to AC as well. So you can do that. So we use just another electrical engineering construct, but we usually look at battery as a DC source, but this could very well be just any kind of power supply, DC power supply that you have. Series circuits like this, there's just a single path for current through these. You have multiple resistances. The total resistance in this is just the sum of whatever that is. So if these are each 100 ohm resistors, the total resistance is 300 ohms. Really simple relationship in a series circuit right there. The current is the same through the entire system. So the current here, anywhere is identical. There's one path. The current is set by the total resistance in this, using our friend George's law. You can see here, it's this voltage divided by the total resistance will give you what that current, and that will flow through each one. And then the voltage drop across each of the resistors, V, will be the sum of that. So as if they're the same, all the resistors are all the same value, all three voltage drops will just be a third of this. But this gets into what you can do, right, is now, if they're different values, first you solve for the total resistance, get the current, and then the current times the individual resistance will give you the voltage drop across that component. And that's how you get to what's the voltage drop across that LED and resistor circuit, and then you use that to calculate the power. So that's one. That's the most basic DC circuit. The next is a parallel circuit. So the loads are in parallel, and this is where this little, this relationship between the resistance, the total resistance, and that is as written there. I won't read it out to you, but the main thing you need to know is if you have parallel paths, the overall resistance will be less than any one of the legs. It may not be intuitive right off the top of your head, but think about it in terms of, again, use that water analogy. If I have one path for water to run, then I add another pipe in parallel with it, the water's going to say, oh, well, another path. Now I have, twice the space to flow through. So electricity works the same way. Electricity will follow the paths of least resistance, and if you offer more paths in parallel, then total resistance goes down. And when we start talking about how you wire your track in particular and getting power, current to an individual spot, this relationship will make more sense when you see why do I need multiple feeders? Why does everything I read or watch on YouTube tell me I should put a feeder every 6 feet or something like this along the way, right? It's because of this relationship that when I add parallel paths, the total resistance to that current is going to go down over time. And then, so this here in a parallel circuit, there'll be potentially different currents in any of these. So instead of all current being the same in all these different places, you have the total current that's flowing here and here, but then each leg may have a separate current, and the total is going to be equal to the sum of all those legs in there. And then the voltage across each of these legs is going to be equal to that, because that's the source across it. So both of those things those are the basics, but there are very few real world situations that are actually exclusively one or the other. The majority of circuits, and this is what you'll see on a model railroad, are really combinations of series and parallel circuits. So you can split it up if you're trying to solve. And the goal of here is not necessarily that you're going to be really solving for current and voltage and all of these again, but you want to understand this relationship. But a series parallel circuit, in particular, one that looks like this, is more what is realistically. So we've got a bus wire. I'm going to use DC as an example here. The same would be for a straight DC layout. It would be the same thing. So you got your bus wire, and then you have the rail that's in parallel with that in a lot of places, because you take a feeder off, you come out of your command station with a bus wire, and then you run a feeder off to the rail. Now the rail is a conductor that's in parallel with your bus wire until you get then to some more track feeders and rails that are in parallel, maybe in series with that, but in parallel with each other, until you finally get down here to what you're really trying to power, which is a locomotive. I'll use that as an example, but if you're doing accessories or things like that, same type of thing. So this is why a lot of common advice that's given out, and it's good advice, about take your, you run your bus wires, but then have multiple drops, multiple feeders that will distribute that out to your layout. And one of the big reasons for that is the difference in the conductivity, or in a case, your the resistance, your wire, your conductors have resistance to them. Copper wire has much lower resistance than nickel silver rail does per unit of length, right? So by putting, we were talking about in parallel circuits, by putting these things in parallel, that total resistance now is much lower. So the point is, of all of this, is that you minimize all of these resistances so the maximum amount of your voltage is available at the locomotive. That's the real goal of this. So our DCC systems nominally put out about 15 volts. We want to make sure as much of that 15 volts as possible gets to the locomotive. That's really the goal. So we want to minimize the resistance in all those paths that lead to the locomotive. We can do that. We'll talk about conductors themselves by minimizing, you can minimize the actual resistance per foot of the bus wire, and we'll talk about that in a little bit. And then avoiding using the rail as the main conductor is the best way to minimize that, because you don't want to buy rail based on the conductivity of it, right? There are a lot of other reasons why you want to choose your rail, so you can avoid having that be an impediment to the flow of current to your locomotive by using the proper bus wire, and then again feeders, right? And then I'll digress a little bit here. One place that's a real problem is connections in rail. In particular, rail joiners are mechanical devices, not electrical connectors. That's why you'll see people, pundits, whatever, recommending, a feeder for every rail or something like that. You want to avoid relying on the rail joiners as conductors. They get loose, they become poor conductors. They just add resistance into your circuit here and make, again, less energy available at your locomotive for that. So, any questions about this stuff? Am I going too fast? Is it too basic, or not too much? Okay, so I'm gonna move away from the electrical engineering piece a little bit and get to maybe some more practical applications. So I've heard also from a couple of people about how do I measure it? How do I measure this? What does it mean? And what are all these crazy dials and nutty stuff on this thing that I bought from eBay here? So digital multimeters are the ones that mostly what you get now. They're pretty good, and even the cheap ones are pretty good. Like this is I bought this one off of Amazon. It was on sale for $32. It lists normally for $40, and it's perfectly fine for everything we'll do. You can spend thousands of dollars on them, and what you're getting for that money is accuracy in the reading. We really don't need it. You want what we're doing in model railroading, we want to know whether it's 12 volts or 2 volts. You don't really care whether it's 12 volts or 11.99 volts, right? It's so these, I would send, don't spend a ton of money on don't spend more than $50 on a digital multimeter. And, and like I said, this one's on Amazon, I think Kiwatt or something like that. They're all Chinese knockoffs anyway, and it's perfectly good for that. If you have an older analog meter, works perfectly fine. The only problem with those is you have to pay attention to polarity, because if you hook it up backwards, it'll peg the meter the wrong direction. You'll just have to switch. It generally won't hurt it. But these digital multimeters, they're auto sensing polarity, so you connect it and it'll just tell you if it says it's negative, you just have it hooked up backwards. But again, it doesn't matter to you. You just do that. And then as far as using this thing, there's usually the next slide will show it a little better about how to use it. Just remember, there's these key points. If you're going to measure voltage, you do it in parallel. You put it across. If I go back to my slide, if I want to measure the voltage available here, I measure like that, in parallel with that load across it. Right? If I want to measure current, you do it in series. So you actually have to break the circuit to put your meter in series, so you connect it so the current flows through the meter in that regard. And then here's a key too. Resistance, you have the circuit has to be de-energized. Your own meter won't work properly. On a digital meter, it won't damage it, but you really can't trust any resistance reading you take on an energized circuit. It just won't work. So you have to de-energize it. The other thing you have to be careful too is if you're trying to measure resistance in here, there's parallel paths, right? If I say I want to try and measure the resistance across that, well, the meter is actually, it's got a battery in it, you'll see, and it puts an ohm meter, works by measuring current, really, by inducing a current into the circuit you're measuring. And what will happen is if I put an ohm meter across here, I'll get not only current flowing here, but I'll have current flowing around here to the meter too. So it's a little wonky trying to measure. But the main thing we're going to use an ohm meter for in model railroading is continuity checking. You want to know, do I have a short, or do I have a short where I expect it not to have a path, or do I have an open where I expect there to be a path? And again, it doesn't matter what the reading is, whether it's 100 ohms or 1,000 ohms. You just want to know if it's flowing. And most digital multimeters now have a continuity function, which usually has a buzzer on it, which is really handy because you don't even have to look at the meter. You set it up to the continuity function, and it will, if it's got a path, it'll beep at you. You don't even have to look at it. I set mine up on the table and I get under the layout and I can, just listen, if it works or not, if I have it. Or, it also, if you're going across, you want to check for shorts as you're wiring up track. If you get the beep, you need to go back and look for an issue here. So this is a little bit more about that. So kind of an eye chart here. I'm not sure you can see. So these are just, what I was talking about as far as how you hook the meter up for these. But you can kind of see here. This is an example. So this is basically measuring resistance. So they've taken that resistor out of the circuit, so it's only got one path here. Most of the meters have multiple places to plug in the test jacks. They're labeled A for current. They may have a common, they may have separate commons for the, and then they'll have another jack for voltage, resistance and thing. It's usually, you have everything for current, and then you have a connection for everything else. You have one for current, and then one for everything else. You take the dial, you set it to whatever the function you're looking to measure is. Omega is the common symbol for ohms, is Greek letter omega. You see that? That's, is the engineering symbol for ohms here. V for voltage, A for amperes, instead of using the I, what you have here. And then this illustration has some kind of sub text, like that's a diode. That's looking for a ground. That's like a high level of thing. The big three that you need to think of are resistance, voltage, and current. And you probably won't use current very often because it's kind of a pain in the neck to try and break the system, the circuit down. I used mine the other day. I was trying to find out what the stall current was on a motor. So, for putting in a DCC decoder, sizing a DCC decoder, and I used it for that. But that was not on my layout. That was like on the test bench kind of thing. You won't use that. Big ones you're going to measure are voltage and resistance and thing. And again, when I get to resistance, I say that continuity. Does it have a path or doesn't it? You don't care too much about those. So like this meter will measure, for $32, it'll measure frequency. There's half a dozen other things that I've never used on it. What it won't do is measure track power from a DCC system. Because DCC is not DC, the actual power that's on the rails. It is actually AC, a funky kind of AC. It's not even like the AC coming out of your wall, but it varies at too fast of a rate for that DC meter to measure. So if you're trying to find out if you've got power, to your rails, DCC power, your typical digital voltmeter or analog voltmeter for that is useless. There are other devices. Some of the DCC manufacturers sell them. If you want to know exactly what it is, it's upwards of like $150, $200 for a. I tried to win one there was one in the raffle. I was like, I could use that, but I wasn't going to pay $200 for it. But if I could have got it at the raffle at the convention, it would have been fine. Rob's got a neat little thing that his is just it's a voltage tester. It's just a couple of LEDs that tells you yes, I've got power there, or no, I don't. But yes.
In my experience, if you set the voltmeter to AC readings, it's good enough.
Is it? Well, you actually get a. Okay, I hadn't tried that, but yeah, it's again, probably good enough to tell you whether you've got power or not, and it doesn't tell you.
There is a product that's called our amp meter that measures actual true RMS.
RMS, yeah. So
DCC voltage, and they're within a couple % of agreement, just a standard cheapo voltmeter.
Yeah, I'll have to try it, give that a shot. I've never tried it. Yeah. RMS is an abbreviation for a mathematical way of expressing AC voltages, an average of the AC voltage. But good, thanks. I'm going to give that a shot when I get home and see how it works on mine. I hadn't. So. If you are buying a digital voltmeter, they usually come with a couple of straight probes like this, which are okay, but I'd recommend spending the extra $10 or so on Amazon and getting a little kit that has all these neat things like alligator clips, and these are little spring clips with a kind of little hook on them that you can attach to these. The bad thing about the probes is they're only going to stay in contact while you're holding them. And if you want to, if you need to manipulate it, you don't have a handy helper around to do that for you. Those alligator clips, and I use these little spring clips probably the most of anything, because they'll grab right onto your rail. It's like it's a little spring loaded. You press the button, the hook comes out of the end, release it, and then it retracts around whatever you have it when you release the spring. And like I said, you get these things. They're really fairly inexpensive and quite handy. The other thing, when you're using the ohm meter or the continuity tester, one of the things they taught us in technician school, one of the first things, always test your meter. Right? Before you start, take and just short your two leads together, whatever you're using, and see that the meter's giving you a short. You should expect it. You should get a short, 0 resistance or close to it. If it reads 1 or 2 ohms, don't worry about it, right? It's all intents and purposes, it's 0. But that way you'll be sure that your meter is working properly. One of the biggest things that happens to these, the battery dies. And you could be out there testing all day, oh great, no shorts whatsoever, and your meter's not functioning properly. So it's an easy way. It's a habit, but it's a good habit to be in. Test that meter. The actual thing, when you're measuring voltage and current, frequency and things like that, all the battery is doing is powering the display and that thing. The actual measuring power to do the measurement is coming from the circuit you're measuring to begin with. So you don't need it so much, but yeah. Good thing to do, test your meter, and might save you some grief in the long run. Here, did that. Okay, another more. So conductors and wiring. Conductors, what we use the term for anything that conducts electricity, and most likely that is some form of wire in our cases, or rail is the other thing. There might be some other ones. So wire in the US is usually sold by American Wire Gauge. You'll see it AWG or just G gauge, and you buy it, and it goes like 0.00 to 30. I mean, it gets really small into the high 30s kind of thing. And if you've ever wondered why it's inverse, when they first started doing it, the wire's made by drawing the conductive metal, copper or some copper alloy, through a die. And you can't go from, say you've got a chunk of copper that's 1 inch in diameter, you can't go down to a fraction of a millimeter in one die. So the gauge is actually the number of dies that successive dies that has been drawn through to get from whatever the original size was down to the size that it's sold at. So if you're buying 10 gauge wire, it's been drawn through 10 dies to get there. 22, 18, 22. So that's your trivia. For if anybody, you go to a bar trivia night and they ask, why is wire gauge inverse to the size of the wire? That's the reason. And the American Wire Gauge has been around since 1857. It's the telegraph company that was the first one to standardize this. Conductivity in a conductor is the inverse, just straight 1 over the resistance. We used to In the US, we used to actually measure it in mhos, M-H-O-S, which is just ohm backwards. But now it's made the SI unit for it is Siemens, so you'll see that more often than mhos anymore. But sometimes you'll see, conductors rated in conductivity or Siemens. Just understand that it's just the inverse of the resistance. Most wires usually ohms per meter, foot or meter kind of thing. You don't really have to pay a lot of attention to that detail of it. The thing to do, so as wire gets smaller, the resistance gets higher. Think of the water analogy again. As you make the pipe smaller, it takes more energy to push the water through that smaller pipe than it does. Same way with electricity. So, and then that means less of the energy in that fluid or current gets ultimately to your load or locomotive. So, in general, if you're like, what do I need for a bus wire size? I can do anywhere from 18 gauge to double aught, which is, this giant stuff like this. In general, the rule of thumb is err on the larger conductor within limits, right? You don't want to, one is cost, more copper, it's going to get more expensive. But say, I can use 16 or 14, you'll probably be happier in the long run if you went with 14, right, type of thing. 12, if you've got bigger layouts, 12. I've heard of people using 10 gauge wire. That's kind of like a Chris Oliver huge, big layout kind of thing.
12.
Pardon me?
He uses 12.
Is he used 12? Okay, so he's even made that. And 12 is pretty heavy duty as it is for model railroad. I'm using 14, and that's probably overkill in N scale. 16 will work. I think anything less than 16 for a bus, a DCC bus, is probably, you're not going to save a lot of money, and it's probably more headache than it's worth in there. But when you can, bigger is always going to be, from an electrical, conductivity size is always going to be better than that. Again, but there are other, cost is certainly one factor, but ease of working with it is another too. If you get on both ends of that too, I mean, you can get bigger conductors. You don't want to try soldering 12 gauge feeder wires to code 70 rail, right? I mean, you're going to end up with a puddle of plastic and probably not a very good joint to begin with, right? The other thing, a lot of discussion about solid versus stranded wire. From an electrical standpoint, the same gauge wire has the same conductivity, whether it's stranded or solid. It's just, instead of one in a solid wire, you've got a certain cross-sectional area for that in one piece of metal. In a stranded wire of the same gauge, you just have multiple wires, and the sum of their cross-sectional areas adds up to what would be a solid wire. The big differences are, stranded wire is much more flexible and easy to work with. If you have like an application where it's got to move, like our N-scale group, we have a gate, that we lift, so you can access the inner side of the thing. Or if you have like a swing gate on your layer or something, it's better to use stranded for that kind of connection because, it doesn't have the coat hanger effect, right? On a solid wire, right, you're gonna, every time you move it, you bend it, you work it, harden it a little bit, and at some point it'll break. So that for flexibility, stranded wire makes it easier to use. I find it pretty fiddly to work with, though. You know, you pull it off the spool that you buy it on, and all it wants to do is, you know, flop all over the place and not stay where you want it. Solid wire, on the other hand, will, if you straighten it a little bit, and actually if you pull it just a tad, basically you can pull it through your fingers, and it will tend to straighten. It won't straighten it, you know, arrow straight, but it'll tend to keep that shape. And also when you're wiring it, moving it around your layout, it'll tend to maintain that shape that you put it in, or at least make it easier. So, I mean, there's advantages to each. Right? I use mostly solid wire, just because I find it, especially when I'm doing wiring under the layout, it's a lot easier to make it neat, and that's we'll get into that because of that property of staying where you put it, kind of thing. When you buy wire online, you usually see it. Besides the gauge, you'll usually see a voltage rating on it. That's actually the insulation, the rating for the insulation. And you probably won't find anything under 300 volts, which is fine. I mean, you're not paying anything. You don't need to certainly you don't need to go anything higher than that. If you find a good price on 600 volt wire, go for it. It doesn't really matter. It's just the point where the insulation starts to break down. We don't have anything close to what the rating is. But if you see that, you know, on your buying wire on Amazon or eBay or something, if it's 300 volt, you're fine. You know, I don't know if you can find it. If there's 150 volt wire, go for it. I mean, manufacturers don't tend to they don't want to stock all this different stuff. So I haven't seen anything less than 300 recently. Here, neatness counts in this. When it'll make your life so much easier in the long run if you can do your best to keep your wiring neat. As you install it, because dollars to donuts, at some point you're going to have an issue, and you're going to want to check where be able to tell where the wire that is causing this issue is coming from, and it'll be a heck of a lot easier if you have some semblance of order in the wiring you did. So establish a color code and stick to it. I know that I got at least one place on my layout where I broke that rule. I didn't stick to it because I needed I wasn't going to buy another 100 feet of wire from one of these. So I put a label on it and said, it's like this wire is blue kind of thing. But yeah, this is just, it doesn't matter what it is as long as you write it down and can keep track of it. So that's just an example of what I did. Red and black are pretty common for track feeders, or white and black. Doesn't matter which one's which. Again, you want to have some conventions that you can remember. Excuse me, and stick to, especially for things where it matters for polarity or phase, like on your rail, your DCC bus and your feeders. It's always good to actually match your bus wires and feeder wires to the same color, right? So if you're using black and red for the bus wire, use black and red for the feeders. Smaller gauge, but the same color. So if you have a short and you look under your layout and you say, oh, I've got a red feeder connected to the black bus, you probably got a good indication of where that might be. And then just other applications, but again, color code is a good thing to start with. Try and plan from the start your wiring. Think of it, I wouldn't say nobody ever does it, but everybody starts with a track plan, right? You know, very few of us just start, I'm going to start laying rail, right? And if they do, you probably abandon that pretty soon after you know. Likewise, as you're doing that track plan, think of how you're going to wire it. And, you don't have to have an elaborate thing, but a sketch that matches your track plan. Do it right on the track plan if you want to, but it'll make your construction easier, and also, one of the other things is start installing. This is before I put the sub-road bed on my layout. I did this is a power distribution cable. Kind of hard to see, but I ran my bus wires in here while all of this stuff was accessible from the top. And it was so much easier than trying to drag those wires, as I'm, underneath the layout like this. So, I mean, you're going to get to a point where you have to do it with the deck installed. But if you can think about it, like, where's my bus wires going to be? How am I going to get the power there? Where are the boosters going to be around the layout? I mean, some of those issues you don't have to worry about on like a smaller layout. Mine's only, the longest run is like a little over 16 feet on it. But a Chris Oliver, I use his because he's the biggest layout I know around the area. But I'm sure he has boosters distributed around that layout, because get back to our DC circuits, even with the bus wires, right? The longer they get, the more voltage drop you get. And you can avoid using a larger conductor for your buses if you actually put the booster closer. There's nothing that says your boosters can't be all over the layout room, right? Yeah. So that's another way to maximize that power that gets to your load, ultimate load. This whole wiring from the start won't be disastrous if you don't think about it. Just make your life a little bit easier, possibly. If you're planning a new layout, I recommend it. Use the appropriate size wire for the application. We kind of covered that before. When in doubt, use the larger size. Right? It'll can save you some headaches in the tank. Group your wires. Don't. So again, it'll probably work fine if you just take everything and bundle it into one giant, conglomeration and wire. But if you have to go back and troubleshoot it, it'll be a lot easier if, this is my turnout control over here versus this is my track power over here, and here's my signaling cable over here. Group the wires together. Zip ties are cheap and a great way to keep things together. You bundle these functional groups, and I have some pictures towards the end where I'll show you some applications of this. There's all kinds of nifty kind of hangers that work with zip ties and even some other stuff that's, so you can stick them on the bottom of your layout, and you can, they'll hold the wire in place, and they'll keep it from dropping down and, snagging on your head every time. So there's lots of neat kind of devices available for organizing wire underneath the layout, and label liberally, so you can remember where things are, what they are. I numbered all the turnouts on my track plan, and then if I go under the layout, I've got a cable tag with that on the bundle for that switch motor control that matches. So I know, this bundle of wire goes to turnout X over here. They're nothing fancy. Labels are like $5 per pack of several hundred. They're just little adhesive things that wrap around the wire. You don't have to get fancy. You don't have to print out anything. You just write the number on them. But again, it's about it. It'll all go together easy. But 5 years from now, when a switch motor stops working, and say, which wire out of these thousands down here, and even on a small layout, it gets big numbers of conductors quickly. Right, so just some things there. What do I got here? Here's some, some tabs. These are just some of those devices. These are adhesive, on the back of these. This one, you slip your own zip tie through, it just sticks up there, and then you can, slip a zip tie through it, lay the conductors here, and, I got a picture of some of them. And then these are neat because they're reversible. They're the same kind of function, but you can clip them and unclip them, right? A zip tie, they're cheap, so it's not a catastrophe, but if you want to add another wire to it, you got to cut the old one off and put a new one in. With these, they like unlatch, and you can see a little bit better there, like that. Here's one of my cable labels up here. Here's some more of them over here. Movement label, this kind of stuff. So that's wiring. So any people questions on conductors, things like that? Okay. So connections. So the other thing, so we get the wire pulled to where we want it, and then we have to connect it to different types of things. So there's some some common types of things that we use. IDCs, insulation displacement connectors, suitcases. People call them suitcase connectors. If you're trying to find them, you want to buy them, search for insulation displacement connectors. That's what technically they are. And they work by basically cutting through the insulation on the side. When you crimp it down, what it's doing is driving that blade down, and it's basically separating the insulation and contacting the conductor there. And then usually what you have is there's actually, two of these slots, right? There's one for both conductors that you're putting in there. So that's the insulation displacement part of it. I highly recommend not buying the Chinese knockoffs in IDCs, suitcases. I've heard a lot of people, have trouble with suitcases. Some people, I hate those things, they never work. I'll venture that a lot of it is they got the cheap ones. It's like, the quality of them, if you buy the 3Ms, you'll be fine. You'll be happy with them at least. Maybe you can still mess them up, but it's a lot easier to mess up the cheap knockoffs because the molding on the case is bad. Sometimes they use some funky metal for the blade, and it instead of going down, it likes to do this. It likes to flop over, So I personally think that the name brand. This is a place where a name brand is worth the little extra expense on that. Pay attention to the gauge specs. If you buy an IDC, it'll say usually say the typical ones we want will be listed as tap connectors. So they'll have a run through. It'll list a run, and that's the bus wire. Say you're doing this on a DCC connection. They'll have the run is the bus wire, and it'll have a range of wire gauge. Say it's good for 12 to 16. And then the tap will have another range. So the tap may be good for 18 to 22, something like that. It's really important to pay attention to that number for the application you have, because that'll be another. You may get them to install, but if I go back to this, I could get this thing to crimp down on a wire, but if it's not rated for that gauge of that wire, it may not. If the wire's too small for it, it'll feel great. I mean, I'll tug on it all day long, and it won't come out, but it never penetrates the insulation, so you have no connection there. So it's a place to, you'll save yourself a lot of grief if you buy the right connectors for the size of wires that you're using. And they come in ranges too. I mean, you don't have to have one for every separate wire you have. Here's a case where you can save some money. All you need is a pair of slip joint pliers to put them together. You can go out and spend $50 for the suitcase tool, but you really don't need it. You get a pair of, I emphasize slip joint pliers, because the jaws, when you open them up to the, you ever thought, why does this, you ever come to I finally found an application why they get wider, right? But when they close, the jaws are pretty close to parallel on a slip joint plier. Channel locks suck for this. Don't use channel locks, because they close at an angle like that. And the point is, you want the blade to go straight in, and the slip joint plier will pretty much do that. Or the tool, I mean, if you want to, the tool is absolutely parallel as it closes on there, type of thing. And then if you're buying them, pay attention as they're listed. TAP, which is a TAP is again, the application you use for a feeder, where you have basically a drop off and you'll look at them and they'll have the run will be obvious because it's got a double end on it, and the tap line is blocked on one end. And make sure as you install that, you push that tap wire in until it stops all the way there. And then you should be, I like them. I think they're reliable. If you do them, if you pay attention to them, they're reliable. They're relatively cheap. They're easy to install under a layout. I mean, it gets a little, can get a little, odd in there. Yes, sir.
Chris Oliver had showed me something when I was at his place years ago. He uses a type where he has the standard, suitcase connection on the run, and then the feed is attaches with a spadler. And those are handy because if you ever find out that you have a short, you can disconnect and put them back together easily.
Yeah.
And they're just as easy.
Yeah, that's a valid point, and I've seen people also use a separate splice connector for the same thing. You can add another, disconnectable and reconnectable type of connector on the splice for that exact reason. It does make a lot of sense.
Yeah.
Again, you get a lot, and I'm not a big fan of just slip-on spade lugs, because I've had, and that's, personal, I've had problems with them because they loosen up and they pull off, and, but I mean, it is a way to do it, again. They're mostly, I shouldn't say, they're mostly reliable. Personal experience. Yeah, well, I'll get down to that.
For isolating circuits.
Pardon me?
We use that same thing in Chris Oliver type of taps with the spades in the museum layout, and we use it a lot for isolating a circuit.
Yeah, just pull them off.
If you got an area you want to diagnose, or you're cutting in, like when we had an added train controller, we put in a third bus line. It made it super easy to take the taps and put them on the other ones without having to cut off suitcase connectors.
Yeah, there's definitely a very practical reason to make that basically that tap connection.
You gotta make it very careful when you put the crimps on.
Yeah.
So they don't come loose.
Yeah.
I tried the same idea with, you're going to get the Wago connectors next, where I use Wago connectors, and
for the taps in the tap. Yes.
Yeah. And the only issue I had was I worried about how much resistance I was, breaking the bus constantly. I would use like a 3-pin, bus in, bus out, and then tap, or even a 5-pin if I have all the feeders, or 5 slot. But I'm worried about building up a little bit of voltage loss along the bus by breaking it all the time.
but I don't have a big of a layout.
Yeah,
And
I mean,
find that, but the other thing is that you can obsess about this stuff, because either, when you wire it, it's either right or it's wrong. And, you don't go back 2 years later and find you
absolutely.
cross-wired, you know what I'm saying?
Yeah,
So-
that's a good one. Yes, I've seen the Wagos used for that, and
Yeah.
I'll get in for the people that don't know what a Wago is. That's, a good segue into the next type of connector. But yeah, that's a great way to do it.
Well, you can also use it, you can also tap one time off the bus and use a Wago for if you have a bunch of feeders going to frog juicers or
Yeah,
whatever. That's where they're really useful.
I'm a big fan of Wagos. I love them.
Yeah.
So we'll go right into that. But as far as resistance, again, you've got to have a lot of wire before those connectors start. Connectors are made to be low resistance,
Yeah.
as opposed to a rail joiner that's not a connector, right? So if you're using it for as intended, the resistance you're adding is pretty small. So unless you've got thousands of them in series, yeah, I don't think you're going to have a lot of problems with that. So lever locks, and this is Wago is a trade name, and Wago's like the Kleenex of these lever lock connectors, right? But it's a kind of a neat name, so that's why I used it in the title, right? So I discovered these things myself not that long ago, doing some wiring, but this is a lever lock connector. And what Wayne was talking about was this in particular. They come in probably hundreds of different connector size, so you can get side by side. They are NEC code compliant. You can use these to wire your house. They're code compliant. They're written right into the electrical code right now. And
not to divert, but I use them inside out with boxes now. With wire nuts.
oh yeah, they're so much easier than wire nuts. They're a little more expensive than wire nuts. Yeah, but yeah, so much easier to install. And basically, it's really simple. It's basically, you do have to strip the conductors as opposed to a suitcase where you just do it. But you strip it back a little of insulation, you open the lever, you stick the wire in, and you snap the lever closed. This is a godsend for work underneath your layout. And I've used them in a ton of places. And what he was talking about is on that tap line, these, I think they're like 18 cents. You're going to get them in like less than a quarter a piece. They're not expensive. I should say, this is a place where I think the Chinese knockoffs are fine. They're, Wagos can be, the brand name Wagos can get a little pricey. But these, you can buy them on Amazon, like 20 cents a piece for these things, and then you can do that. They come in dozens or maybe even hundreds of different configurations. These up here, they're like the one into, I think there's 4 or 5 different ones, so you can take one conductor in instead of using like jumpers. They're already internally jumpered, so all the blue outlets on that are jumpered together. So you can make a lot of easy things. You can get individual ones that snap into, I'll talk about this DIN rail in a minute. So there's just tons of different configurations. Make wiring super easy, reliable, safe. I don't have any downside that you've used. Sounds like you've used. Can you think of a downside on them?
Oh, the Wagos?
Yeah.
No.
Well,
you have to, I'll just say this one thing. If you go to Home Depot and see things with like wave connectors, be careful, because some of them don't have levers. And you shove the wire in and you have to.
Oh, you have to
cut it and put a new one on it.
Yeah, like if you do, after I told you not to, but if you wire a socket, 115 volt socket, it's got like a spring loaded, pin on the side. You can you shove the conductor in and it grips it, but you can't get it back out. You can't. It's made so it won't come out. But maybe there are, but I've bought all mine off of off of Amazon, you know. Lever, and there you search for lever lock connectors as opposed to Wagos. You probably get the knockoff ones when you search for Wago as well. But, okay. Screw terminals, I'm not a fan. Easy to screw up, pain in the neck to work with. You know, if you don't use a lug, then you got to do it right. Got to make sure you have the hook in the direction that you're tightening the screw, or just a lot of ways, a lot of failures. Hard to work with under the layout. Lugs are notoriously, hard to do well. You got to buy the tool. Don't do it with a pair of channel locks, or you will regret it eventually if you do enough of them. They work. I mean, hopefully I'm not don't offend anybody if you wired your layout with screw terminals and lug and it works fine. There's nothing wrong with it. I just starting new, I had the opportunity to use different kinds, and I decided, although I'll show you a picture that I did use some screw terminals before I discovered Wagos, and so I was using that. But
very labor intensive.
They are. They're labor intensive and error prone type of thing. So DIN rails. DIN is an acronym, German acronym. It's the equivalent of ANSI, American National Standards Institute. It's the German national standards. They have a ton of standards that are out there, widely used in Europe, and in the U.S. But a DIN rail is actually this is a DIN rail. It's an extruded aluminum bar, and it's got this kind of, you can see the shape here, and it's made, it's like they call it a top hat rail. It's made to connect devices to. It's a mounting device. So you take this rail, and I screwed it to a piece of plywood, and then all kinds of different electrical devices snap right onto it. So you don't have, this is the aux power supply. It's a 12-volt power supply I used to power my switch motors off of that. Just snaps right onto the rail. It's got like here, you may be able to make that out. These are made to snap onto a DIN rail. So I can take all these individuals, and I'll show you a picture of that, and I can make, how many terminals do you want? Do I want 10? Do I want 50?
The right-hand picture shows.
Oh, perfect, thank you. Yeah, you can see, well, this shows how you install the wire, and then, these, they just snap on. You don't like it, you want to take some off, take a flat, head screwdriver, put minimal amount of pressure on it, and it pops right off the DIN rail too. They're just super, again, very easy to use. Make it, very flexible. The only downside I could say about this is it's kind of a pain in the neck to cut this with a hacksaw. Which you can, and which I did, but it's about $150 for the DIN rail cutter, and I didn't have enough to do for that. Maybe as an organization we could buy one and then share it.
Dremel tool with a cutting disc.
Pardon me?
Dremel tool and a cutting disc.
Yeah, I tried that, and I found it just as fiddly as the hacksaw. The problem with the hacksaw is this stuff is really soft, and the blade's constantly, getting hung up in it. But it's a really neat, convenient way to mount these electrical devices, and it's not just Wagos and level locks. It's power supplies. I mean, think of an electrical device, relays. You'll be able to find a version of it that'll mount to a DIN rail, or in the case of some of these, right, like these, they come with this little adapter that snaps onto the side of that and makes them either or. So you either can just screw it, to something, or you can use the adapter and then it's down DIN rail. And let's see. I wanted to slightly touch on soldering. but not too much, because soldering's another thing that could be a whole nother clinic by itself. But if you go to the NERX from last year, I think it was March, March, and you go to 12:23 in that minutes, 12 minutes and 23 seconds into that. There's a gentleman from, I think he's from New Brunswick, he's from the Canadian, Eastern Canada division. He did an excellent clinic for that on soldering. And he's a professional. He's been doing it as a technician for years and years. And he's got a really good clinic there on soldering in particular. Which, once you get the basics down, buy some decent equipment, and it's not as hard as it is. I wouldn't recommend it for doing it under the layout. That's why lever locks. But like I saw my switch motors, circuitrons, I used all 8 connections on them. I soldered the pigtails on my bench, and then where'd I go? Oh. So I soldered the pigtails to them, I clamped this to my workbench, soldered these pigtails on it, then made myself an 8 terminal block out of a piece of gin rail and some of those lever locks, and that's how I installed them under the layout like that. So soldering, you definitely want to do in there. So when I have any, that was all I intended to say on soldering. So definitely watch that clinic if you're interested in it. Connections, I think I covered pretty much everything there. This is just an example. I put this in here, some more connections. Here's some more. These are 3-pole splice type of lever locks, and I was using them to do frog power. So you can see I come off of the feeder buses to one side, and then one goes up to my frog. One cuts down from the frog, and just an easy way again to wire some of this stuff. This is the back, that terminal or that control panel that's on the first slide. This is the back of it, and this is the advantage of solid wire. Right? There's nothing, there are no wire ties. There's wire ties down here, and this kind of wraps messed up. But solid wire, it stays. You bend it, and that's 18. I think that's 18. No, that's a bit smaller. That's 20 gauge wire. It's not even that heavy duty, but you bend it, it tends to stay where you want it. Pre-Wagyu. When you use that again, might even change it. And then this is there's 50 terminals on there, and it was all individuals, a piece of DIN rail and 50 terminals. It makes it so easy once you get this installed to make those connections, things like that. There's just some other things, stuff we talked about. Diagrams, make a drawing, for both your, it'll help you during the installation, and it'll help you get rid. It's one of the requirements for the AP certificate. You have to have a schematic. This is how to wire a switch motor for a right-hand turnout with the fulcrum facing the points, kind of thing, because it's slightly different depending on how for my application, how you do it. So just a little diagram there. Just some other examples of trying, once you get started installing feeders, you get a ton of them, right? If you follow the guidelines of how many you need, I don't know, I haven't got a good way to say you can make track feeders neat, except, if you, maybe keep them short, not too short though. I mean, that's do what you can on track feeders, but eventually, especially in a place like a yard where you have a lot of parallel tracks and things like that, you're going to end up with, you know, kind of a rat's nest of wire from the feeders. You can do, but you can save yourself some headaches if you take the other things and, you know, group them together. Like, you know, like I took the 8 different connections from a switch motor and, you know, put a tie around those so that, you know, and then labeled it at the other end as a, so you don't have to have super fancy diagrams. I made that one. Haven't put that in CAD yet, but that's just, you know, how to wire the switch motor on mine. That's the, what else we got? Oh, just some resources. Books. I brought this one. I think this is an excellent book here. Was called back, now it's Fire Crown, written by a guy, Larry Puckett. He wrote the DCC Guy column in MR for years. He's got a YouTube channel. You can, if you see him, and most anything by a reputable publisher in print, you can usually, you know, trust, you know, any of the magazines, RMC, MR. Videos, buyer beware, right? There's a lot of good information out on YouTube. There's a lot of crap too, and more AI generated stuff. So, you know, I call it, it's kind of the Wild West of DIY. I mean, if you go to trains.com and get something produced by, you know, the model railroader guys, you can be pretty sure that you can be sure that it's high quality.